Alright guys, so in this video I want to teach you about different types of collisions and the types that we're going to see in this class. Now this does connect with momentum because remember we said that even in a collision, momentum is conserved. Now we're going to talk a little bit first here about energy. Now we haven't done conservation of energy yet, we'll do that next semester, but right now you should be aware of something called kinetic energy. You've probably talked about that before in a previous science class, maybe back in 7th or 8th grade. Kinetic energy is the energy of motion. And any object that has mass and speed will have kinetic energy. All right? The more mass that there is, the more kinetic energy it has for a given speed. The faster it's going, the more energy it has for a given mass. Now, we can put this all together in an equation that is that the kinetic energy equals 1/2 mv squared. And you may have even seen that before, where we have 1/2 multiplied by the mass of the object. Like I said, something bigger with the same speed will have the same mass, and then times the velocity squared. So the velocity is actually a little bit more important than mass here, but they are both important to calculate that kinetic energy. Now, most of the time, when things collide, energy is lost. Now, how is it lost? Well, energy can be lost in a variety of different ways. Energy can be lost due to sound, right? And that's one of the things we'll talk about next semester is how exactly does sound work? What is it? Well, one of the things that sound does is it transfers energy, right? The way that sound works is that something causes the air to vibrate, and the air vibrates, and then it causes your ears to vibrate. Now, in order for that to happen, there's got to be some energy there. And so sound requires a transfer of energy. So kinetic energy can be lost if you hear a sound. Now, sometimes energy is lost as heat, right? Like when you rub two things together, there's some friction going on. Energy can be lost as heat because that's a different type of energy. Now, sometimes energy goes into deformation, right? Like when you have a car crash, those two cars are going high speeds, or maybe one of them is going a high speed, and when they run into each other, the cars get messed up. They change their form, they change their shape. That's what we call deformation. And so that can be where some energy goes. So energy can go into all of these different things, right? But the point is that kinetic energy in a collision does not have to be conserved. You can lose kinetic energy. Now, that's what we're going to talk about right now. Most of those situations where we have a collision is what we call an inelastic collision. Now, in an inelastic collision, kinetic energy is not conserved. All right? Now, you may remember that when we talked about momentum, we said that the sum of the momentum's initial has to equal the sum of the momentum's final. And that's what it meant when we said that momentum was conserved. Well, in most collisions, the sum of the kinetic energies before is not equal to the sum of the kinetic energies after. And if those two kinetic energies are not the same, then it is what we call an inelastic collision. Now, there is a special type of inelastic collision called a completely inelastic collision. And in a completely inelastic collision, not only is kinetic energy not conserved, but the objects actually stick together. Boop. Now, we've actually seen some of these already, right? Remember the example that I gave of me skating down rolling down the sidewalk on my skateboard and running into a kid and grabbing that kid, and we move along at the same speed? That is an inelastic collision because me and the kid move along together. We stick together afterwards. Now, they don't have to be completely stuck together, just need to move along together. The example about the dirt being poured into the train, that was a completely inelastic collision because after the dirt collides with the train, they move along at the same speed. So that would be a completely inelastic collision. So if the two objects stick together, then kinetic energy will not be conserved. Anytime that it is inelastic like that, anytime it's completely inelastic, the kinetic energy will not be conserved. The initial kinetic will not equal the final kinetic. And now we do want to look at a very special situation, which is the elastic collision. So in an elastic collision, kinetic energy is conserved. Now, of course, what that means is that the initial kinetic energies, if we add them all together, will equal the final kinetic energies. Now, most of the questions that we look at in this class, we're going to look at momentum first because momentum is always conserved in a collision. And then with the information we have at the end, we will determine if kinetic energy is conserved or not. And so we're going to be doing this idea of we're going to check the sum of the kinetic energies before and the sum of the kinetic energies final. And we're going to calculate that kinetic energy by doing 1/2 mv squared. And you'll notice that it needs the same information as momentum. Momentum needs mass and velocity as well, but this is a different relationship between mass and velocity. These are both important quantities. Now, we're not going to dig into this too deep right now. We just want to make the understanding that in some collisions, energy is conserved, and in some collisions, kinetic energy is not conserved. Now, I keep saying energy is conserved, but energy is always conserved unless it's turned into mass. Sometimes energy is, quote, lost, but in those situations where energy is lost, it's just turned into something else. It's turned into sound, heat, changing the molecules in the object. That would be deformation. All of that can be somewhere where the energy goes. All right, now we're going to go ahead and move on and look at a couple of examples now. So let's go on to the next video. All right, guys, here we go. We're going to do a couple of examples, and the hope is that you'll get comfortable with this new idea of types of collisions and kinetic energy. While shooting pool, Armand strikes the cue ball with a speed of 3.5 meters per second. It strikes the 8 ball with a mass of 0.5 kilograms and comes to rest. Find the speed of the 8 ball and show that the collision is elastic. Now, first, recognize it's giving me masses, it's giving me speeds. So we want to say, okay, this is probably not kinematics or forces. I don't have anything about forces or accelerations. So probably not forces. That leads me with the speed and the mass to say this is probably a conservation momentum question. And so I'm going to start off because I know that momentum is conserved in a collision, and there's definitely a collision going on here. I'm going to go ahead and start with my table for the collision. All right, so let's go ahead and put that in. There we go. Now we're ready to start throwing some numbers in. Remember that this is all for momentum, and momentum is the mass times the velocity. So when I look at the cue ball, the initial mass was 500 kilograms, so 0.500, which will be times its velocity, which was 3.5 there initially. And that should give me a value of 1.75. Now, that 1.75, I do know the units are kilograms meters per second because my 0.500 was in kilograms. My speed was in meters per second. That's units for momentum. Now, the 8 ball initially has its mass, which is 0.500, and its initial speed, which if you've ever played pool, you know that it starts at rest, and so that's going to be 0. Now, when I add these together to get the total initial momentum, I'm going to have 1.75 kilogram meters per second. Now I'm going to look at the final. Now, it does say that the cue ball strikes the 8 ball and comes to rest, which means it is going to be 0.500 times the speed of 0 because it comes to rest. The 8 ball has a mass of 500 times its new speed, and so when I add those together, it'll be 0 plus 0.500 v. And so we know that the sum of the momentum initial has to equal the sum of the momentum final as long as there are no external forces. Now, there might be a little bit of friction here, but remember, in the time of the collision, there's very little time there, and so we'll say that friction is basically not doing anything. The normal force and the gravity balance each other out, so they're not going to come into play. So therefore, momentum should be conserved here. All right. So we take the sum of the initial momentums, which is 1.75, and that should be equal to the sum of the final, which just ends up being 0.500 v. And to solve for v, we divide by 0.500 on both sides, and we should then get 3.5 meters per second is the final speed of the 8 ball. And so we found the final speed of the 8 ball. Yeah, got that. Now the question says, show that the collision is elastic. Now we learned in the previous video that if something is elastic, that means that the initial kinetic energy should equal the sum of the final kinetic energies. And so if you want, you can create another table like this and do initial and final for the kinetic energy of the cue ball and the 8 ball. Okay, you don't have to do a table, but if you want to, we can do basically the same thing here. All right, so we split it up. This is now going to be kinetic energy, which is equal to 1/2 mv squared. And then we'll fill in the same things as before, just like that. And then we'll go ahead and put in that 1/2 mv squared. So I'm going to do 1/2 times the mass of the cue ball, which is 0.500, times its initial speed, which is 3.5 squared, 1/2 mv squared. And so if I multiply those, the 1/2 times the 0.5 and then times the 3.5 squared, I get 3.0625. Okay, so I'm just going to write that down here. 3.06, we'll go 3.06. And then the 8 ball is going to be 1/2 times its mass times its velocity squared, which is just 0 there. And so I do end up with 3.06 kinetic energy in the beginning. And we're going to do the same thing for the final. So we're going to go 1/2 times mass times its final velocity, which remember was 0. So that's going to be a 0. And then 1/2 m, sorry, that should be 500, times that v, which is 3.5 squared. And again, I run that in through my calculator, and I get that same 3.06. And so I've showed that the kinetic energy before and the kinetic energy after are exactly the same. Now, it doesn't have to work out like this. It did because the cue ball and the 8 ball have the same mass, and that's something that happens sometimes when you have a perfectly elastic collision with things that have the same mass, is one stops and the other goes with the speed that the first one had. You may have seen this before in those Newton cradles, if you've seen where it has like the balls that just kind of hang, right? And they hang like this, and the first one strikes, and then the last one swings up, and then it swings down, and then the other one, and the middle ones basically stay where they are, but the ones on the ends move. That's because it's basically an elastic collision. That's why it goes for a long time, because most of the kinetic energy is conserved, and it's transferred through this idea of momentum. All right, so there we go. We were able to show that it's elastic by showing that the kinetic energy is the same in both situations. Let's move on to the Here we go. So this time we've got a gun which is firing a bullet with a speed of 400 meters per second. Determine the speed of the kickback of the gun and determine what type of collision is demonstrated. So here we go. The first thing that we should do is we should recognize that this is going to be conservation of momentum. We've seen this example before, and so we're going to go straight into our momentum table. And I'm going to go ahead and fill that out real quick. You can do it as well. Pause the video if you need to. Ta-da! And you'll notice that I even put up here in this top corner, I wrote that momentum to remind me that this table is for my momentum here. All right, now I'm going to go ahead and put some numbers in. The gun at first is at rest. So the mass, which would be 4.2 of the gun, times its initial speed is 0. And then the bullet, which its initial mass is 50 grams. Please remember to turn this into kilograms. So that's 0.050 times its initial speed, which is before it's shot. So also at rest. So you'll notice that both of these guys are going to give me 0. And if you need to pause the video and work through the math yourself, that's fine. That's why we're doing a video. So you can go through it at your own pace. All right, so I end up getting 0 plus 0. That should be my total momentum initially. All right, now the final momentum will be the gun, which is going to be its mass times, it's asking for the kickback, the speed of the kickback, so that's V, right? So V is the speed of the kickback of the gun, and then the bullet is going to be that 0.050, its mass times its velocity, which is 400 there. And so we're going to go 400 times 0.050, which is going to be equal to 20. And so it's going to be 4.2 V plus 20. So I just defined, you got to be careful with this, I just defined this to be positive, which means I'm saying that the bullet is flying to the right. So therefore, hopefully, the gun is going to have a negative and it's going to be going to the left. Let's go ahead and solve. The sum of the initial momentums needs to equal the sum of the final momentums. The sum of the initial momentums is 0. The sum of the final momentums is 4.2v plus 20. Subtract that 20 to the other side, and I got negative 20 equals 4.2v. And when I do 20 divided by 4.2v, I get about 4.76 negative meters per second is the velocity of the gun. So it's got a bit of kickback there. All right. Now, the next question is determine what type of collision is demonstrated. Well, we had three kinds, right? We had inelastic, completely inelastic, and elastic. Now, we can already take out completely inelastic. Remember, completely inelastic meant that after the collision, they moved along together. They kind of stuck together. That's definitely not the case here. So it's either elastic or inelastic. Now, the only way to find out is by finding out if the kinetic energy is conserved. Is it the same before and after? Now, actually, in this situation, you don't even need to do the calculations because we know that initially they were both at rest. Remember, kinetic energy depends on speed, right? If there's no speed, there's no kinetic energy. So therefore, initially, the sum of the kinetic energies initial is 0. In the end, then we end up having some kinetic energy, right? And so we would not say that this is an elastic collision. It would be something else. Now, technically, in an inelastic collision, we expect energy to be lost. So really what we're being introduced to here is kind of a fourth type of collision, which is what we call super elastic. Now, in a super elastic collision, we end up with more kinetic energy than we started with. So the better answer is to say, well, it's super elastic, but if it's definitely not elastic because energy is not conserved. We don't have the same amount of kinetic energy before and after. Okay? If you have to choose one of these three, we'll go with inelastic. But a better answer here is super elastic to say that we end up with more kinetic energy than we started with. Now, where does that kinetic energy come from? Well, it comes from the energy, the chemical energy that was inside of the gunpowder that caused the explosion and caused the bullet to get moving. So there we go. We were able to answer that question without having to do major calculations. All right. Now, in our final example, we actually are going to need to do some calculations, but this will be our last example. So here we go. This time, the speed of a bullet can be measured by shooting it into a large block of clay and measuring the resulting speed of the block. Okay, so we've got a bullet being shot into a block. So here's bullet, here's block. Afterwards, the bullet and the block move along together. So this is before, this is after. Now, hopefully you're recognizing this is a collision, so we're going to make a table for our momentum. So here we go. We've got the bullet, which was 0.05 kilograms. Notice that it is in kilograms. We don't know the initial speed, so that's what we're going to put for V. That's how fast was the bullet traveling before, so that's going to be our V. We do know that the block initially, which has a mass of 10 kilograms, is at rest. And so therefore, my total initial momentum is that 0.05 V plus 10 times 0, which is 0. The final momentum is going to be that 0.05. Now, it does say that the bullet embeds into the block of clay, and they're going to move along together at this point. And so if the block is moving with 3.7 meters per second, then so is the bullet. The block has a mass of 10 and is moving along at 3.7, and so therefore we can put those two together. I'm going to go ahead and punch that into my calculator right now because I can. So 0.05 times 3.7, and then I'm going to add that to the 10 times the 3.7, and we should get 37.185. Now at this point, I can make the sum of the initial momentums equal to the sum of the final momentums because during a collision, the momentums are conserved. And so I end up with 0.05 v is equal to 37.185. And that should be easy enough. Just divide both sides by that 0.05, and we get that v, which was the initial speed of the bullet, is about 743, we're going to round that, 744 meters per second. So it was going pretty darn fast there. All right, great. Now the next question is find the change in the kinetic energy and determine what type of collision this is. All right, so this time we can't cop out by just saying, oh, we know it's completely inelastic. Yeah, we know it's completely inelastic because the two stick together, right? So it's definitely going to be completely inelastic. All right, now the question is, what is the change in the kinetic energy? So we're going to need to figure out how much kinetic energy there was before and how much kinetic energy there was after. Now we can do that using a table. You don't have to use the table, just like for momentum, you don't have to use the table either, but it's sometimes helpful. So here we go. Now remember to find a change. Anytime you find a change, the change in the kinetic energy, it's the final minus the initial. That's just what a change is. The change is how have things changed from what they were before. So it's always final minus initial. So we're going to go ahead and find those numbers now. So we're going to start with the bullet. The bullet had an initial kinetic energy of 1/2 times its mass, 0.05, times its speed, which we just found out was 744 squared. Now the block had no speed, so 1/2 mv squared is just going to be 0 there. And so I can add those together to get the total kinetic energy at the beginning. So 0.5 times 0.05 times 744 squared, and we do expect a large number here, is 13838. Now we haven't talked about the units for energy yet. We'll get there, but it is something called joules. Now what we're going to do is we're going to find the final kinetic energy. So again, we're going to do 1/2 times the mass times the speed. Now the final speed was 3.7 squared. And then for the block is going to be 1/2 times its mass times 3.7, its final speed squared. Now I do have all the speeds now. This is why we did momentum first, because momentum allows us to get the speed. Momentum helps us find that out. You can't do that using the kinetic energy because we don't know exactly how much kinetic energy was lost. But we're now at a point where we can add those together. So we're going to do that 1/2 times 0.05 times 3.7 squared, and we're going to add on the 1/2 times the 10 times the other 3.7 squared, and we get a total of 60, if I round to the nearest whole number, 69 joules. Now that's a lot of energy, right? But energy is going to be lost. You're going to hear the bullet smack into that clay block, right? There's probably some heat. There's a lot of friction because that bullet has to go from 744 meters per second to rest. How is it doing that? Well, it's slamming into that block. It's drilling a hole into it. That's some deformation there. Remember, we talked about deformation, changing the bonds and how the molecules are connected there. And last of all, there needs to be something where there's probably some friction in there as well. It's going to heat up. There's some energy lost. So a little bit of everything there. We do want to find the change in the kinetic energy, which is the final minus the initial, 13838. And if we do that, we should get a final value of about negative 13769 energy units, joules. And it should be negative because a lot of energy was lost. The negative just represents the fact that we've lost some energy there. All right? And that's the end of example number 8. The fact that the kinetic energy is not the same before and after confirms that it was inelastic. We knew that because they stuck together. If they stick together, if it's completely inelastic, it is definitely not elastic. All right? So there you go. That ends the examples. I hope this is helpful. Make sure that you're able to use these in order to finish your homework tonight. All right.